Hi everyone, we are back and we are going to talk about linear viscoelasticity. So we have talked a lot about isotropic linear elastic materials. So isotropic linear elastic materials. We've also talked about anisotropic materials as well in lecture 6, looking at all of those complex tensors. But we have been focused purely on the elastic response, elasticity. But there are some materials, specifically polymers, that while they do have an elastic response, they also have an additional response. They have a viscous response, hence the I misspelled that there, viscoelasticity. So if the viscous response is a flow type response, it's a liquid type response mechanically. There's also an elastic response, which we all know good and well, of a solid. So this is very important because that response, whether it's a flow or an elastic response, depends on timescales. It depends on temperature, and polymers and lots of other materials, it depends on rates as well. They have this thing called time temperature equivalence. So this is a very, very important basically property that's very unique to polymers and the elastic or the mechanical response of polymers. So we're going to be looking at basically this time, rate, and temperature dependence on the mechanical response of polymers. So time, temperature, rate. So we're going to look at a property called linear viscoelasticity, an elastic solid response, a viscous fluid response. The viscous response is a time component. Elasticity does not, as we see in that equation here. There's no time component here. There is for the viscous term. Elasticity has that reversibility as well. So we need to look at this concept of viscosity. So viscosity you've probably seen before in fluids and other courses. So our shear stress is related to our viscous term. It looks Hookean if you just look at that rate, but we have that time dependence. So you could think of this as, again, we know viscosity of peanut butter is more than that of water. So if I pull faster, my shear stress increases, but that viscosity essentially remains the same here. And additionally, if I have a high viscosity, I'll have a high shear stress as well. So it's going to be harder to pull, again, my plate through peanut butter than it is for water. So if I pull faster through water, my shear stress increases as well. So again, it's similar to Hookean, type spring, law. So we can see that there. We can see essentially that shear force growing. But again, if you have a fluid, again, if you actually slow down to zero, you'll just get no recovery, and it's just zero shear stress because you'll just get flow. So when you have a material where the viscosity is independent of strain rate, so specifically when the viscosity is not dependent on that strain rate, we will call that a Newtonian fluid. So you've dealt with those previously, but polymers are typically non-Newtonian. So the viscosity is not a constant, but can depend on the strain rate or the total strain. And you'll see one of my favorite YouTube videos when we get into class. So some materials can, basically the viscosity can decrease. So those are thixotropic materials. Rheotropic, the viscosity increases of fluid flows, like blood or printer ink or cornstarch. Viscosity also has a thermal dependence too, an Arrhenius relationship. So viscosity will decrease as temperature increases. So next time we'll get into that time temperature equivalence. Thanks. Bye.